Good morning, and agenda for today is ensemble learning. What's ensemble learning? Ensemble learning is, can be combined a collection of base learners or algorithmic models, which can be combined to form a better prediction or a better learning context. And typically, we combine. So it's essentially a committee of experts, a collection of learning learned models or learning models, which will be able to do a better job than the individuals. So that's the agenda. So essentially, how do you make sure that a collection does better than the individual learners? We typically combine what is called weak learners, which we are going to see a little later. Idea is to combine the classifiers if you're an typically these kind of ensembles are applied in classification algorithms. That doesn't mean that you cannot apply ensembles in other forms of learning. So in ensemble classifiers, what happens is, can we combine classifiers to improve the performance? All right. So ensembles of classifiers, and when you combine classifiers, say for example, I've got 5 classifiers, and out of which I'll do some sort of aggregation, and then the aggregated result given by these 5 classifiers becomes the result, the ultimate result given to the outside world. So when you combine classifiers, there are typically two types of approaches. One is weighted voting and the other is unweighted voting. Voting, you know that if there are 5 classifiers and we have a binary classification context, say class 1 and class 2, and there are 5 classifiers. So 3 classifiers says this is class 1 and 2 says class 2. Since the majority is class 1, you say like the assigned class is class 1. So this is called unweighted voting. Everybody is given equal chance, and everybody's out is counted alike. Right? That's called unweighted voting. Weighted voting is some of the classifiers may be given more weight compared to others. Their decisions will be given more weightage compared to others. So these are the two types of aggregation mechanism used in ensembles. So when you have a collection of classifiers, how you combine them, right? That's what it is, and can be done either with an unweighted voting or weighted voting. We're going to see both cases later. And whom do we combine? We combine typically what is called weak learners. Weak learners are learners, or in the case of classifiers, these are classifiers which are slightly better than a random guess. So, for example, so you have a classifier which is point, which the accuracy of the classifier is say 0.52. You call that a weak learner because see 0.5 is, I mean, I've got a two binary classification context. Either it can be class 1 or class 2, and yeah, without any training I can say what you call the possibility of the what you call a random test point being classified as class 1 or class 2 is 0.5, which is a random guess. If your classifier is little but better than a random guess, you call that classifier a weak learner. Can you combine weak learners to form a better ensemble classifier? All right, that's idea. Otherwise, classifiers which produces presumably or probably good accuracy, which is much above the random guess, is typically labeled or is generally labeled as strong learners. So this is the idea, general idea of ensemble classification. We have original training data, and you can create multiple data sets. So there are different ways in which these multiple data sets. So from the same data set, you can either sample with replacement. You can actually use the same data set with a different weightage for every point. There are multiple ways in which there are various ways in which you can generate multiple data sets on the same data set. So for example, I got 100 points. I can sample with replacement, meaning I take a sample and I put it in my D1, which means, and at the same time I'll reconsider the sample again. So I've got 1,000 points. Let's assume that the data set is 1,000 points and my D1 sizes are like I can fix it at 1,000 or 500 or whatever, and that's my data set size. So I keep sampling from the original data set with a replacement, which means that same data set can participate in multiple times. So one set of say 500 samples or 1,000 samples taken from D1 from D will become D1, and another sampling will give me a D2, another sampling will give me D3, etc. up to DT. So I have T data sets, and I'll build a classifier in each of these a classifier. I'll build a classifier with each of these data sets, which means that I'll train, this is my original training data. These are all training data sets generated from an appropriate procedure from the original training data. And I'll train multiple classifiers on each of, like, with each of these data sets, I'll train multiple classifiers, and ultimately I can combine the result primarily. So this will be like this ensemble, this collection will be the ultimate, will be treated as a classifier. So we have got classifier with T participating weak learners. And so when a new test point comes in, what happens is, like, I'll give the new test point to each of these classifiers, and each of these will give me a decision, and ultimately I'll combine the decisions of each of these classifiers. So this is called an aggregation phase or a fusion phase or decision fusion phase. What you do is, the simple decision fusion can be a voting. So I'll take a majority vote among all the decisions of these classifiers. The binary classification problem, I know, like, some classifiers, a majority says it's class 1 or either class 2, then I'll go with that decision. So the combine operation or the fusion operation of the decisions would be, the simplest case can be voting. All right, let's see an example. It's a weather forecast. All right, so I've got yeah, there is a reality. This is basically a cloudy day and a sunny day. Right, these are the classes. It's a 2-class context. So it's a cloudy day, either it's a cloudy day or a sunny day. And I've got how many examples? 1, 2, 3, 4, 5, 6, 7. I've got 7 samples. This is a testing context. I've got 7 samples, right? Some data, and the associated labels, the reality labels are given here. So the first sample is representing a cloudy day. Second is a sunny day. Fourth one is again cloudy. Fifth is cloudy. Sixth is sunny, and seventh is again sunny. And these are the training, essentially the labels given by the test data. All right, the original test data. The test data has data points. The 7 points has labels like this. And these are classifiers. I've got how many classifiers? 1, 2, 3, 4, 5 classifiers. And our combination operator is a majority voting. So let's look at it. So the first classifier says this is a cloudy day, and third one, fourth one, and fifth one. And only second classifier says this is a sunny day, which means that among the 5 classifiers, cloudy decision as a cloudy day takes majority. So we'll decide and combine, and this particular mechanism will combine. See, there are 5 classifiers, out of which 4 says it's cloudy and 1 says it's sunny. So you decide as cloudy. So is a case here. Majority is sunny, and majority is cloudy, and likewise. So this is how you take decisions in a typical ensemble, right, with voting. So it's a majority vote model. Majority vote, choose the class predicted by more than half if it is a binary classification. Basically, you go with the majority class. That's what it is. So if P is the probability that a classifier makes an error, right? If P is a classifier, that is the probability that a classifier makes an error. Assume the classifier errors are independent, all right? So the probability that K out of N. Have you seen this distribution? All right. Have you seen this distribution anywhere? So the probability that K out of N classifiers make an error is N choose K, P raised to K1 minus P raised to N minus K. So have you seen this? Anybody? What is the distribution? What is the distribution? N choose K, P raised to K1 minus P raised to N minus K. Binomial, yes. Yeah, so it's a binomial distribution. So meaning error is considered to be, like, the probability of the error is actually P, which means that it's considered to be the counter thing, which is the success or whatever. So K out of N being chosen with probability P. So P raised to K1 minus P raised to N K. So therefore, the probability that a majority vote classifier is in error is, say, if I have what do you call, N choose K, P raised to K1 minus P raised to N minus K is basically K, and K can run. Right, K can run between, say, if you have got more than N by 2, right? So what does it say? What does it say is basically, like, it's a majority, right? So N by 2 is where the half of N. So if K runs, so the probability that the majority, so when will the classifier, the ensemble will go wrong? Ensemble will go wrong when the majority says it wrong, right? Ensemble will go wrong when the majority is like k can run between. That means out of n, k, which is greater than n by 2, right, or n by 2 plus 1 or whatever, it's n by 2, right, n by 2 to n, you sum it over all those possibilities, right? K can run between n by 2 to n, and all those possibilities you sum over the individual what do you call individual value of k, and then what you get is an error, right? So numerically you can say, suppose there are 25 base classifiers. Each classifier has an error rate of 0.35, which is slightly better than the random guess. So which means that 65% of the time the classifiers do well, right? Assume the classifiers are independent. Probability that the ensemble will make an error is basically, so 25 by 3 plus 1, that's what I said, right? So basically n by 2 plus 1, 13 to 25. So if out of 25 classifiers, if the ensemble has to go wrong, 13 out of 25 has to go wrong, or more than 13 has to go wrong, right? 13 plus. So 13 to 25 classifiers, right? If there are 25 base classifiers, 13 to 25 are summed over 13 to 25, 25 choose I epsilon. So this will approximately come to, if you put this value here, it will come to approximately 0.06, which means that, what is the meaning of this? So individuals are giving us an error rate of 0.35, right? But the ensemble is able to give us an error rate of 0.06, which means that 99.4% accuracy for the ensemble when you combine weak classifiers with only 65% accuracy. So you combine 25 base classifiers with 65% accuracy, and when you do that, the probability that the ensemble will go wrong is only what you call 0.06, which means that, so these classifiers, when combined, 25 of them, when combined, you will get an accuracy of 99.4. This is the beauty of ensemble classification or ensemble learning, right? Ensemble will always do better than the individual ones. So value of ensembles, why do you do this? Yeah, this is a theorem that I think I mentioned a while ago. It's called a no free lunch theorem. No single algorithm wins all the time. That's what the statement is. So there is no context independent what do you call merit for any classifier over any other, right? So you can't say that deep learning classifiers are better than an SVM, or SVM is better than whatever, right, a Bayes or whatever. You can't say that. There is no single algorithm wins all the time. That's not free lunch. When combining multiple independent decisions, each of which is at least more accurate than random guessing, errors can come down. So, and we know that when humans want to take decisions, they conduct committees. I mean, they actually create committees and conduct meetings, right? Meetings, I mean, basically the decisions of decisions taken by a group of individuals is assumed to be better than the individual decisions. That's why we conduct meetings and discussions and then come to decisions. So ensemble, value of ensemble is like nobody is better than any other. So typically you can combine them to get better decisions. So a little more little of math here. Let's assume that the true distribution is of basically like true distribution which connects the data point x, the set of data points x, and the values of the label y. So you don't know the joint distribution. The moment you know the joint distribution, you don't have to do learning, right? You're given only the training data set which somehow captures the connect between the data and the label, and you want to build a model which approximates this joint distribution, is what you typically do in machine learning, right? When you're actually doing what is called generative learning machines, which I've already mentioned a while ago. So p x comma y is unknown to us, and we have training data using training samples x1, y1 up to xn, yn, and which are essentially which are samples taken from joint distribution px comma y. That's what we have. And you have this notion of generalization error. So generalization error is So you know that, right? It's basically, you can take, if A and B are the what do you call, the A is the predicted output by the machine and B is actual label, A minus B the whole square. What is this called? Least square. So we can, if you want to squared error minimizer, right? If you it's basically squared error. It's a squared error. It's an example for a squared error. So what do you do here? So your error is essentially using the samples taken from the joint distribution pxy, and you have this decision function, basically, like, I mean, basically you have the error function which essentially finds the, what do you call, the error between the predicted. If H is a hypothesis, basically this is the model, right? This is a model. H is a model. When given X, it will give you HX, and there is Y. So basically, if there is a difference between HX and Y, if HX and Y doesn't match, then you say that there's an error, and this is the error function F, right? This is what called the generalization error, right? If you can look, I mean, it's something that is very trivial for you. So this is your Y label, and this is your HX, and somewhere it doesn't match. That's all I want to say. It's simple. So I want to introduce a little formal stuff here. It's called a bias and variance. So there is something called a bias and variance trade-off. This is a typical interview question. So be attentive over here. Treat Hx given as has a random function. What is S? S is your data, right? You are basically, like, you have a data set, training data set S, and so it's all it says is essentially you're computing the output of the model for X, right? X, which is essentially a member of the data set, has a random function, depends on the training data set primarily. All right. The expected generalization error is, this is something that we have already seen, over the randomness of S. So S essentially may not have completely captured the joint distribution Px comma Y, but it may have a little randomness. So it may have certain things outliers, certain things slightly off the curve, meaning may not be fully fitting into the context. So that's where there can be a randomness of S. So basically what you do is you have a model H, and you have a sample X, which may have a little of randomness also, right? That's what it is. And what is bias variance trade-off? So let's take the squared error. So it's essentially the loss function. A is actual label, and A is a predicted label, and B is the actual label, A minus B square. Let's take the squared error, squared loss context. Consider one data point. So Z is Hx is essentially the model output minus Y. It's here, and what is this? This is expectation. E is expectation of the error. Right? Let's represent that as Z cap. Let's represent that as Z cap. So you have this is essentially the error, right? Expectation of that error. The notion of error is, you represent that as Z cap, right? And then you can actually find the difference between the expected error and the actual error. All right, expected error minus actual error will be. So what you can do is, so what is this expectation of what is? You can actually see that. So Z minus Z cap. So what you do here is, so you can actually this is the here, right? So you just substitute the value here. So all right. So what you want to do is, if you can take, say, let's say there is a slight mistake over here. I see. Yeah, it's okay. So let's look at this equation. It'll be clear to you now very soon. So let's take the expectation of over the randomness of Z minus Z cap the whole square. So we are taking, I've told you, we are taking the squared loss. So what is Z minus Z cap? Z minus Z. So there's a small mistake over this expression. I'll correct it later. So we are taking the difference between, so Z cap is nothing but the expected error, right? So Z minus Z cap the whole square. If you take it, what you can do is you just expand it. Z square minus 2Z cap minus Z cap the whole square. This can be so we can say that this is expectation of Z square minus 2 into expectation of Z cap. So basically, like, so Z cap is essentially a constant, right? That's where it goes in, and then z cap the whole square. So this can be written as so this is, what is this? This is expectation of z is nothing but z cap, right? 2 into z caps the whole square. So minus 2 into z caps the whole square. This is z caps the whole square. So this will be expectation of z square minus z cap the whole square, right? That's what it is. And if you are taking the expected error, right? What is expected error? I told you expected error is expectation of the error. What is the expectation of the error over the sample? H of x, basically this is the machine given thing, and y is actually the actual predicted, right? So if you compute this will be so what this is essentially, like, we have defined z as this, right? Z as the difference between the predicted and the actual. So it'll be z square, which is essentially x. What is this? What is z square? Z square can be so you can from here you can write what is z square. What is z square? Z square can be written as, from this equation, just go here. What is z square? Expectation of z square will be equal to expectation of z minus z cap the whole square plus z cap the whole square. Do you see something interesting here? Let's remove this. Actually an unnecessary thing. If I don't need this, yeah, that is a problem. So you don't. So let's look at this equation. Have you understood the maths? So I'll repeat the math here. So I'm looking at squared error, squared loss function, and you have a data point xy, and so the error is hx minus y, right? Hx minus y. If you don't want that s conditioned on s, because it's conditioned on the training set. That's only what do you call the notational difference that we have from the previous session. Hx minus s minus y. So z, and I want to define z cap as expectation of z, which means that expectation of x given s minus y. So that's what it is. Expectation of this is actually called z cap. I just want to find the difference between the actual actual error and the expected error. When I expand it, I'll see that what do you call the square of the expected error, which is over here, is basically expectation of the error. My error function is squared error. That's the reason why I use. Instead, I would have written it here. So expectation of the error. This is the error function. Since I'm using the error function, is actually squared, right? Expectation of the error can be written as expectation of z minus z cap the whole square. What is z? Z is the actual error minus the expectation of the error plus what do you call the square of the expectation. All right, and these two terms are defined as variance and bias. So what is this? This is basically, see, what is this? This is the expected error. Expected error computed out of a model, right? The square of the expected error is called the bias. So essentially, expected error, expected over what? Expected over the training points, and that's where you build the model, right? So this can be essentially treated as what do you call a parameter which is capturing the notion of fitness, or to the extent to which, right, if this parameter is low, which means that your expected error is low for a model, which is essentially a statement that you have fit into your training data is well fit into the model. So this is representing what do you call more of the model fitness factor. I'm going to the semantics a little later. And what is this? Z is like if you're computing it for what do you call testing a training point or a test point. What is this? Z minus Z cap. This is basically like I've computed an expected error of a model, and I'm computing the actual error minus expected error the whole square. So this is essentially a variation from the expectation. So given any new point or an already known point, given any new point or an already known point, I'm essentially computing the difference between the error that will make and the expected error. So this is this term is essentially capturing what you call the error expected in a typical testing context. So this you can treat this as what you call a measure of the generalization capability of the machinery, right? So because this is at any moment I can take any point, test it out, and see how it's different from the what you call expected error. So this is to do with more to do with the testing or generalization part. This is more to do with the fitness to the training part. And these two terms are right. That means that I have got an expression. The expected error can be represented as a sum of variance and bias. Bias term representing more of the model fitness to the training data, and the variance term representing what you call a notion of error that is expected in a typical testing or the generalization capability of the machinery. Right? Let's go a little further and see this. All right, if I got a training data, I can actually and I want to fit, right? This is a typical what do you call curve fitting or regression context. I can draw a line like this, right? I can say like, okay, yeah, these are the, I can actually twist it. It's again a line. I can draw a curve like this. I can draw what do you call a curve like this. And I see that, you see this green thing, this can be like thought of as the areas from which typically I should be able to twist the model by changing the parameters, or I should be expecting my data coming from, right, in a generalization context. Look at this, right? Let me play this slide. We'll give you a little more context, right? Let's look at what do you call the plot of bias and variance here, right? In this particular diagram, what you see in the black, right, in the second row, the black one is representing bias and the green one is representing variance. All right, what is expected error? You can see the expression below. Expected error is a sum of bias and variance. Expected error for any model is a sum of bias and variance. Bias is model fitness, and variance is error expected in the when the model is tested with some data point, right? It's a notion of, it captures a notion of generalization capability. And if you look at the first column, right, first leftmost thing, if you have a line fitting that data point, all right, you can see that, say the data point, the train, this is essentially the red ones are your training data points. Line doesn't perfectly fit into those training data points, which means that the z cap square, which is essentially a notion of expected error for that model, the bias parameter for that particular, the leftmost column one, right, it's very high. But the variance is essentially, what is the variance? All right, variance is essentially what is expected, z minus z cap. What is z minus z cap? What is z minus z cap? For any point tested out here, and you know that the z cap is going to be high, but the variation from what you call the expected and the actual will not be very high. Going to the next context, the middle one. The middle one is a little more curve shape. You do some sort of fit, which means that the bias will come down. At the same time, bias comes down, which means that the z cap value will be like moderate. All right, which means that, right, the variation among, when you actually test it out, any context, yeah, you can see that the green is the area from which you can actually, the model can potentially expect. You can see that the variance is also moderate. But go to the rightmost column. In the rightmost column, what is the rightmost column? The rightmost column, you see that it perfectly fits in, which means that the model is I can even say that model is overfitting. Model perfectly fits in, which means that I do have a very low bias, all right? But what is happening here is, it's very low bias, but I know that my data point can get in from any of these, whatever, right? You see that green boundaries out there. I can get into any of these areas. And what's going to happen is, since I have fit in well into the model, what will happen is the chance of that I getting back generalization will be very high. This is a case of low bias and high variance. So in short, I can say that if the model is overfitted, and the model is overfitted, the generalization capability, you can very well expect that the model will have a low bias. Model is said to have a low bias and a high variance. And if the model is basically regularized, meaning if the model doesn't fit well into, like, doesn't do either underfitting or overfitting, but you have perfect sort of a fit, you will have a right balance between a bias and variance. So when you actually train a model, you are expected, just go back to our original slide, your expected error will be a sum of bias and variance. As I've already explained with the math out here. The bias is essentially like the model fit parameter, and this is basically if you fit well into the model, this term will come down, which means that this term will go up. All right. And if the model is the other way around, primarily like you have a very simple model, say for example a complicated context, you fit in a straight line, what's going to happen is you will see a lot of variance, which means that, yeah, any point which is around, I mean, doesn't sort of, so basically like you have a high bias, so you fit a simple what do you call, simple line fitting that complicated context, so you'll have a very high bias, but which means that the variance basically, like, that very high bias, meaning that you have got a high error, which means that what do you call, the variation of the individual points from that high error, right, which is essentially the expected error. So the expected error is going to be will be high for the model, which means that the variation of what do you call, variation of an actual error from the expected error won't be very high, which means that the variance will be low, the bias will be high. So when you train a model, you have to do a perfect balancing between the two. You don't either go to what you call an underfitting context where you make sure that you have a high bias and which results in a very low variance, or don't overfit, where what is going to happen is you will get a what do you call, low bias, but the moment you have a low bias, which means that your error will drastically come down because you fit well into the model, which means that you can't expect your what do you call, your data always coming from that, because generalization is all about performing beyond what is being seen. Sample may not have completely captured the joint distribution, so what's going to happen is this will shoot up. Chances of this getting shooting up, it will be high. So in the case of training, what you need to do is you have to balance between the two, and that's what is being shown over here, right? This kind of a model would be an ideal model, the middle point, right? That's all I want to say, right? This is the context. So in general, bias is contributed by the training error. A complex model has low bias because it will fit well into the data, and then there is what do you call, a high variance caused by feature error. Essentially, like it's a measure of generalization performance. So you typically get a question on how do you, I mean, you can't get a model which has low bias and low variance, which is very, very difficult. Right? What typically happens is you have to do a trade-off. That's why this is called a bias variance trade-off. When you're training a model, make sure that you regularize model in such a way that you reduce your expected error. And I'll tell you a little more into this, because see, bias is essentially like, this is to do with training, and this has a lot to do with the complexity of the model. If you have a highly complicated model, which means that your training data will well fit into the model, right, empirically, and you'll get a low bias. All right. So if your model is too complicated, your structural complexity of the model is too complicated, you may end up in a low bias, which essentially can result in a high variance. All right. In the other case, if you're taking a simple model, your structural complexity of the model is very low, right? That means that complicated context, you are fitting only rather than a curve, you are fitting a line. So if your structural complexity is low, it can result in a large Z cap, which means that your variance will be low, but the bias will be high. All right. So that's what is called the bias variance trade-off. And bagging can, and see, basically, like we are going to see, bagging is a kind of ensemble classifiers which can essentially reduce the variance in base classifiers. So bias variance trade-off is a typical problem in the learning context. So bias problem, the hypothesis space may be made available by a particular classification method, does not include the true hypothesis, is what bias problem is, which means that the hypothesis space is a set of all functions which essentially captures your notion. Your neural network model is not complicated enough to capture your model. right? You may remember our original diagram of fx. If your f is not enough complicated, yeah, you may end up in a underfitting context. And variance is the hypothesis space is too large, which means that for the amount of training data, so your training data don't have enough of points, then what is going to happen is the selected hypothesis may be inaccurate on unseen data. So bias is more to do with the training part of, and the complexity of the model, and variance is more to do with the testing or generalization capability. So if you have a very complicated model, you may end up in a low bias with a high variance, and if you have a very simple model, you may end up in a what do you call in a high bias, right, high bias and low variance context, right? So you have to do a trade-off between the two, and that's what typically a regularization does, right? That's what the notion of regularization. So ensemble methods that minimize variance, there are ensembles are typically, I've told you that ensembles can bring in error down, right? From, I've told you that a classifier, for a class V classifier, if you combine 25 V classifiers with error rate of 0.35, you have seen that the error rate drastically coming down in an earlier example. So this ensemble typically works around this bias variance trade-off. Bias variance trade-off is essentially like, how do you get the right mix between what do you call the bias and variance? How do you find what do you call the community of experts such that you can actually address the notion of bias and variance trade-off, right? That's what ensemble classification is all about. This is a theory behind ensemble classifiers. It's only for those who are really interested in the math side of it. So there are mainly types of ensemble methods, right? So ensemble methods that minimize the variance, and ensemble methods that minimize bias. And ensemble method, and we'll be looking at both these one algorithm from each of these categories. Backing or bootstrap aggregation is one ensemble method, which essentially reduces variance, which essentially what it does is it creates a committee of experts where every committee member is a specialist on certain things. And you can, and there is another type of what do you call ensemble method, which works on the complexity of the model. How do you weigh the model accordingly enough with enough complication, or how do you combine models in such a way that the model complexity is at control, and you can try to minimize bias to have a control over the error. So error can be controlled by a proper trade-off between the bias and variance. And this ensemble, the backing kind of ensembles typically works at the variance side, and ensembles such as boosting, which we are going to see, works around the bias side. This is again for those who are interested in the theoretical aspects. Right? Let's look at backing. That's what is that's your university stuff. So this is very simple. Bagging is very simple. Sampling with replacement. You have got original data, bagging. So you got what 10 data points. What you can do is you can essentially what do you call it? You can essentially sample, right? I bagging round one. I can sample 7. The first, right? I have how many points? I've got 10 points. I can sample from. I got at first sample I got for the first data set D1 is 7. I got 8, 10. 8 can again participate. So this is sampling with replacement. So I stop the sampling when I got 10 points. So this is the second one. The third one, I can actually do that. All right. And then what I have got 3 data sets. You remember this? I'll just go to that slide. Right. So D1, D2, and D3 is what we have to do right here. I've got D1, D2, and D3, and then so each of the sample has a probability. If 1 by n is a chance that, say, out of n data points, I'm choosing or what do you call? I mean, basically, I'm choosing 1, right? Each sample has a probability of 1 by 1 minus n raised to n of being selected in the test data. So that's what it is. And training data is basically like 1 minus 1 by 1 by n. Right? Basically, I mean, the original. Basically that's what the so what I want to say is 1 by, you know, that chance of getting selected is right. So I mean, since you are taking what do you call n times the samples, I can actually take 10 samples of this kind. So you get to this kind of probability value, which is basically like, so with an example, this will be a little easier. This method also called 0.632 bootstrap method. This is called bootstrap aggregation or bagging. So sampling with replacement for creating data set of the same size. That's what bagging is all about. And then you combine. A particular training data has a probability of 1 minus 1 by n of not being picked up. So this will, so you understand what is, so when you are actually like creating the training data D1, so 1 by n is the chance of getting picked up, 1 by 1 minus n is not being picked up. That's the probability of ending up in the test data basically is, right? So of not picked up, which means that it is not a part of the training data, it is not selected, is ending up in the test data, meaning not selected or not included in the training data is 1 by 1 minus n, and that has to happen, right, n times. You do it n times. So if you what do you call, approximate, it will come to e raised to minus 1, it's 0.368. So which means that this means that the training data will contain approximately 63.2 of the instances at any point in time. That's what is being shown over here. Same stuff here. All right. So the training data is 1 by 1 minus n. That's what I was showing. All right. So you can look at that math. So what I want to say is this again, another term for it. 0.632 bootstrap is nothing but which says that it's nothing but bagging. It's another name for bagging, and this is how the name comes in. So so for example, this is an example for bagging. So we want to find a collection of 10 simple threshold classifiers. Threshold classifiers is like I choose a threshold. So I've got two classes. All right, the extremes, right? I can say +1 or -1 or whatever. So this is some plus point -1. So I have two classes, -1 point, -1 labeled point and +1 labeled point, and I take a number in between, right? So each sample based on the threshold I assign to +1 or -1. So if my sample that I get is 0.5 and my threshold is 0.6, so 0.5 I say like it belongs to -1 because it's less than my threshold value. Otherwise the what do you call, otherwise the point belongs to. So basically just based on a threshold for any classifier. So any classifier is a simple classifier. All it looks at is like the sample that I get. If it is, so every class will have a threshold value. If the value of the sample is below the threshold, you say to one class, above the threshold to other class. How do you fix the threshold? We can fix the threshold using a lowest error. Say we have got a training data, you want to fix the threshold in such a way that most of the points are correctly classified. All right. So this is basically so I've got this is the bagging round one, meaning I can create numbers, and I'm actually taking numbers between what do you call, say for example, I'm taking numbers between 0.1 and 0.9. It's basically 0. I can assume that 0.1 and 0.9 is my extremes. I'll take points between 0.1 and 0.9. So this is basically yeah, this is I only sample at regular intervals. In that case, my first data point is 0.1. Some sample I've taken 0.1, 0.2. So it's with replacement, right? 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7 up to 0.9 is the original data set I sampled. I get first point and I've got the labels because my threshold for this particular round is I have fixed my threshold as 0.35. If it is less than 0.35, I put to one classifier. Otherwise, I'll put to other classifier. Greater than 0.35 -1. All right. So likewise, I put another threshold and I've got another classifier. Third threshold, I got another classifier. Fourth threshold, these are all classifiers, right? So now I can combine all these classifiers. I get a 0.4. What do? I take the decision from here. I take a decision from here. I take a decision from here, and likewise. So how do I put this 0.35? How do I decide this 0.35? See, if I've got the original training data, I can decide in such a way that majority, right? With my threshold, majority of my points should be correctly classified. So bagging is basically like, so this is what I said. I've got 10 classifiers. Out of the 10 classifiers for a point, touch point, 0.1, I can decide and then I can assign, right? I can assign. So it can be as simple as a summation. It can be some what do you call, sign. It's essentially voting. That's another easier thing, and you can see that this accuracy of the ensemble classifier. So this is a simple classification mechanism based on a threshold, and threshold is taken from the training data. How do you choose a threshold? Fix k in that threshold in such a way that for your training data, current training data, this is the training data for the first classifier. Put threshold in such a way that majority of the points are correctly classified. That's what it is. And if you do it, what is going to happen is you can see that this classifier gives you 100% accuracy. So these are classifiers which, see, you can see that this, basically like these are simple classification mechanisms, and combining these kind of classification mechanism for a random point, some of these classifiers actually like may do a mistake. Say for example, with 0.65 as the threshold, what do you call, or 0.2, some other point, 0.2 or 0.4, the point that is not there here, this classifier may make a mistake, and it means you can easily check that this is better than a what you call a random guess. But combining all these 10 classifiers together, you reach 100% accuracy, which is a good thing. Meaning, all I want to say is it can essentially a committee of experts can essentially do better than individuals. Do better than the individuals. All right. This is another bagging based classifier. This most of you must have heard of. It's called a random forest. Is nothing but these are classifiers. These are ensembles where each member is a decision tree, and typically. When you typically apply these kind of algorithms, you use what is called decision stump. Decision stump is nothing but a one depth decision tree. One depth decision tree. In some methods specifically designed for decision tree classifiers, they're called random forest. And random forest is very generic. It can accept arbitrary decision trees, but the typical context is decision stump. Random forest grows in many trees. Ensemble of unpruned decision trees, meaning decision trees which may be sort of what you call grown as per the training data without much of a pruning to do regularization. Each base classifier classifies a new vector of points in the original data. Final result is classified in the new instance as voting. So random forests are essentially like you have each of these. You create data sets. So you create from this data set, you create what you call a decision tree, and the decision tree you combine. Say for example, I'll go to the original diagram. That's what is going to happen in decision trees. So you have got a training data. You sample with replacement data sets of the same size, and each of these is a decision tree, right? Each of the decision tree, and all these decision trees on a test point will vote, and will decide, and then voting is used to take the decision. And so an ensemble classifiers built with bagging from decision trees is called random forest. All right, introduce two sorts of randomness, bagging and random vector inputs. Bagging is basically like each tree is grown using a bootstrap sample from the data, and random vector, each node best split. You know that. So decision tree is essentially like based on an appropriate measure of goodness. You choose the right feature and do a split. That's called a random vector method. Typically, so this is the picture of a random forest. Original training data. So basically, like you can create randomize what you call data sets, and then create ensembles over here, and then basically like you do a voting to combine decision tree classifiers. This is called random forest. So ensemble of decision trees is called a random forest. So that's another example. Just like the threshold classification, you can combine any kind of classifiers, typically any classifiers. So bagging is reducing variance is what I told, right? Ideal setting, many training sets, train module each on average. So you have this kind of a notion, right? So what you do is you can actually, if you look at it, everybody has, so you have got the training data here, and you sample and create the S dash. You essentially create what you call multiple samples which are specialists. Primarily, like if you look at this data, if you look at this diagram, right? So some part of the data may get covered over here, some part of the data, some part of the distribution may be covered over here. So you are essentially getting a committee of experts, which means that you have somebody to look at every part of the space that you are essentially looking at, and which essentially mean that your combined generalization capability may be better. And that's the reason why typically it's called ideal setting. Many training set, train modules using S dash is a sample taken from that, average the predictions, right? Average the predictions. So you look at this particular context, average the predictions. That's what is happening over an ensemble. So in a typical ensemble, it's basically like the majority is taken decisions. See, if you what do you call, if your approach is a voting, it's majority voting, right? So typically you are looking at working around the predictions. What is prediction? Prediction is all about generalization capability, which means that you don't do anything around the model. Each of the model may be like maybe overfitting, maybe a specialist of each of this model may even overfit, and may even what do you call, maybe a specialist. But ultimately, like when a new thing comes in, the specialist and the specialist and those who are not in the specialist area may also vote, and ultimately you're trying to improve the notion of generalization performance. And that's the reason why, and that's essentially the reason why You say like your agenda is to improve the prediction capability of the machine, which is a part of this, right? Essentially, right, I don't bother a lot about this. I'm trying to make sure that my aggregated decision is better than the individuals. This is what you have seen with a numerical example there. My aggregated decision is better than, which means that will happen only when my error comes down. Error on what? Error of the ensemble comes down, right? Error over the ensemble comes down compared to an individual classifier, which is essentially, that's the reason why we are saying what you call bagging is essentially a method to reduce variance. That's about bagging. All right. Reduce variance, samples are independently. In practice, resample with the replacement, train module, variance reduce sublinearly because S is correlated and bias is increases. I mean, because you have a complicated model, you have more what you call more models to more parameters to deal with. That's why bias is typically like is not considered. So all I want to say is ensemble. So there is a generalization aspect to error, and there is a what do you call model fitness aspect to error. But bias works around the generalization aspect of error. You try to reduce the error by combining maybe a little slightly complicated, slightly more complicated model, and that's the reason why we can understand that it's essentially working around the notion of variance. Right, works well if the base classifiers are unstable. Right, means weak learners increase accuracy because it reduces the variance. Does not focus on any particular instance of the training data, but rather what do you call? I mean, it may even overfit possible. Therefore, less susceptible to model overfitting in the overall context. But individuals can be specialists. Right, that's where bagging is all about. And there is another what do you call ensemble called boosting, and we'll be looking at a very specific aspect of boosting, or algorithm in boosting called Adaboost. Boosting is an iterative procedure to adaptively change the distribution of training data by focusing more. So let me do a recap. You have got training data. You take. I mean, I've got a training data of 100 points. So I create 100-point training data, multiple 100-point training data sets by a repeated sampling of the same training data. I've got a training data. I do a repeated sampling from the training data. I create 3 individual training data sets, and I train a classifier in each of these, and I compile the decisions. Essentially, my idea is to do a better generalization, which is a part of reducing variance, right? And I can also work on individual points, right? Now I've got n points. I've got 1,000 points to train my model. What I do is I create another 1,000 point by sampling, second 1,000 point, again repeated sampling, third 1,000 points. This is bagging. Rather, when I train my model on 1,000 points, right, and when I do a testing, or maybe with a cross validation, whatever, when I test this model, maybe with the training data itself, I see that I have got 1,000 points, and I fit a model. Now I see that some of the points are actually being correctly classified, right, and some of the points are wrongly classified, which means that my model is able to do justice to certain points, is not able to do justice to certain other points. Can we just concentrate on the points for which the model is not doing justice to? Can we just concentrate on, say, I've got a training data and I've created a model, and the model, when I try to test, right, the training data, when I try to test the model, what is happening is, on the training data itself, some of the points are correctly classified, some are wrongly classified. So correctly classified points, I don't have to bother too much, right? It's already taken care of. But wrongly classified points, I have to give more importance. So can we assign some weights to these training points in such a way that points which are not correctly classified can be weighed more compared to points which are wrongly classified is weighed more compared to points which are correctly classified. And such an approach is called boosting. Let's see that. It's a little slightly, so you have got this is the original idea of boosting, but Adaboost is a little different. So you split your training data into x1, x2, x3, 3 partitions. Let's to start with simple. Train a classifier L1 on x1, test L1 on x2, right? Basically, it's again a part of the training data. Train L2, the next classifier, on L1's mistakes, which means that, so out from x2, some of the points may be misclassified. So x2 on the points for which x2 is on the points from x2 for which L1 has not performed. What you can do is you can train L2. All right, now you can test both L1 and L2 on the available the unseen data x3 and train L3 on the disagreements between L1 and L2. Basically, like L1 and L2 agrees. That means that both points in x3 where L1 and L2, these two classifiers are agreed. That means that those points are taken care of. But there are points where L1 says some class, L2 says some other class. What you do is you can actually train a new classifier. So then testing is apply L1 and L2. If disagrees, use the what do you call it? You can check out L1 and L2. New point comes in. L1 is tested and L2 is tested. They agree. You give as a class. Otherwise, what happens is like you leave it to L3. So you give to the third. This is the original idea, right? And if you have to split data like this, you need a large training data to do this. And this is the original idea. And people have worked on further and said like you don't have to split the entire. Say you've got 1,500 points. You can split into 500, 500, 500, and do this. Or you can split into what do you call 600, 600, and another 300 and do this. You can do, but people said, why do you do this? Can we do it individual point level? Can you do it for every training point? And that led to a new interesting classification algorithm called, ensemble algorithm called boosting. Boosting focus more on previously misclassified records. Essentially, n records are assigned equal weights. So let's assume that boosting works by, let's assume that boosting gives importance to every point, and there is the notion of a weight associated with every point. Records that are wrongly classified will have their weights increased, and records that are classified correctly will have their weights decreased. That's the essential idea. So you've got 1,500 points. You at the beginning you will assign every point the same weight, and your classifier will do some job. And after classification, certain points may be correctly. See, basically these points are the training data points, and the training data points, there is a classifier trained, and the classifier do justice to certain points. Those points you reduce the weight, and the points for which the classifier is wrongly classifying them, you increase the weight, and then you will train the classifier. That's the idea, right? Equal weights are assigned to each training instance. Say, for example, if there are n points, 1 by n is the weight for the first round. After classifier CI is learned, you train your model on this particular training data. We'll see like how do you do it. The weights are adjusted to allow the subsequent classifier CI+1 to pay more attention to the data which are misclassified by CI. Right? Final boosted classifier combines the votes of each classifier. You combine basically the learning from all the classifiers, and then you get an ensemble essentially. And Adaboost is one such example. It's stands for what is called adaptive boosting. So bagging is one where you have training data, you create samples of the same kind, multiple models are trained, and then you combine. That's called bagging. Boosting is essentially you give importance to each of the training points or chunks of the training points, and then you say like, okay, I train my data, my classifier on this training data. If some of the points are correctly classified, I can actually like reduce their importance in the training process. Rather, I'll give more importance to the points which are misclassified. And this is the idea of Adaboost or boosting in general, right? Adaptive boosting. Bagging is also called bootstrap aggregation. Bagging or bootstrap aggregation is all about that what you call sampling with replacement and training multiple classifiers. Adaboost is all about giving importance to individual training points and making sure that training points which are misclassified in the training data, the training points which are misclassified from the training data are given more importance, and the classifiers are retrained to get better classification accuracy. Right? That's basically the idea of Adaboost. It's also called adaptive boosting. Right? Popular boosting algorithm. Let's look at the adaptive boosting algorithm formally. Right? You have got training data set D contains n labeled data. So x1, this is what it is. You have got n such points. Initially, I assign equal weights to each of the training data to generate T-based classifiers. That's what it is. You will create T classifiers. Each of these classifiers will be incrementally trained on. Right? If T1 is doing some mistakes, when you train T2, what is going to happen is the mistakes of T1 will be like the points where the mistakes have happened in T1 will be given more importance while training T2. Right? In T2, then you test out the training data, and then you see that some mistakes are still there. What you do is points in the further training of T3, points where T2 made a mistake will be given more importance, and then you do T such rounds. You essentially like kind of train multiple classifiers. Output is a composite model. You get an ensemble, right? Let's see how it works formally. Right? I've told you training data D contains n labeled data point. Initially assign equal weights. Every data point is given equal weights. All right, equal weight. So you got a training data point. Every data point is equal weight. Initially assign equal weight and classify the data points. Let's look at this equation. Even though the equation looks very complicated, it's very simple. So you got a test point, right? Test point can be, I mean, let's assume that it's a point from the training data itself. You're taking the, so what will be the label of the test point, right? Argmax over y, all the possible y's. What you do here is, if CIX test, CI is the ith classifier. You have got multiple classifiers. Let's assume that you've got 3 classifiers trained, which means that T is now 3, 1 is equal to, I is equal to 1 to 3. So CIX is basically, you have a C1X, C2X and C3X. So I is equal to 1. So C1, that data goes in. And if it matches the label, this is a delta function. This is a delta function if there is a match. If there is a match, which means that if the model predicted and the actual label matches, right, this will be a 1, otherwise it will be a 0. Delta function will be a 0. This is a 1 if there is a match, otherwise this is 0. All right. So alpha I is actually a weight associated with the classifier. So alpha I into 1 if there is a match, alpha I into 0 if there is no match, which means that I've got 3 classifiers, which means that I is going to run from 1 to 3. I've got 3 classifiers. Currently, assume that you've got trained. T1 is trained, T2 is, I mean, the first classifier trained. On its mistake, another classifier C2 is trained. On its mistake, C3 is also trained. I've got C1, C2, and C3. I'm combining the decisions of C1, C2, and C3 to give an aggregated, an ensemble decision, primarily like the decision of the ensemble. How do you combine? Combine in such a way that alpha I is the importance of classifier I. There's a weightage for I. We'll come there. How do you compute alpha I? Very next slide has it. So there is a weightage for the classifier I, and if the classifier I, say for example, if you are considering first classifier alpha 1 into, if the first classifier C1 for that training data point, if the training data the classifier provided result and the actual label, if there is a match, this will be a 1, otherwise it will be a 0. Which means that alpha 1 will get added to this sum only when C1 correctly does the job. Alpha 2 will also get added if C2 does the job correctly. If C3 gets the job correctly, right, alpha 3. So for the class, say for example, if that is the case, so this is basically for the Y class. Let's assume that the class, the point that we are considering, we have got a 2 class context, say 0 class and a 1 class. We are actually taking the 0 class. In the 0 class, so I've got a test point. I know that the test point is actually, I've got the test point. The test point is actually 1 class. All right. So for 0, so I'm actually like argmax. So for the class 0, I get, if that, you know that the actual label is a 1. So they have got a binary classification context. Class labels are 0 and 1. Class labels are 0, 1. Understand? Class labels are 0, 1. And we know that my test point is essentially the point from the training data is essentially a 1 point. The point belongs to the class 1. I've got a 2 class context, 0 class and a 1 class. The X text is essentially a point belonging to the class 1. All right. I need to compute this particular thing for class 0 and class 1. I'm computing for class 0. If that is if C1 is essentially like, I know that this Y is actually class 1. And C1 is giving me 0, which means that this doesn't match, which means that delta is 0, right? For 0, this is basically, this is not happening. So for the other class, say this is actually 1, this is 1, all right? For the 0 class, I'm saying like, see, this is 1, which means that only those, so since this is 1, this match will occur only when this classifier is actually predicting correctly. Only when this value is 1 is equal to 1, this delta will be 1, which means that only for that y, this will be like get summed up. If the classifier C2 and C3 is correctly predicting, right, C2 and C3 is saying, hey, the class is 1, which means that alpha 2 and alpha 3, we have assumed that there are three classifiers C1, C2, and C3. Alpha 2 plus alpha 3 will become the maximum, because the other class for the C1 is actually saying that what will be C1 will be saying that, hey, the class is 0, but the actual class is 1, right? Which means that there is no match. This will be 0, which means that you don't get anything. And the C2, what will happen? C2 for the C2 class, what is happening? Right, C2 class, this summation will add up only for 1, because that's where it get added up, because it's for 1, y is 1. So for the 0 class you get a 0, and for the 1 class you get the other one, right? So which means that argmax will be essentially a summation of the weights for the classifier. And how do you get the alpha is the weights of the classifier, right? Classifier weights are computed from their error weights. So C1, C2, C3, they'll have an error rate. Basically, epsilon is essentially the error, where the error rate of the classifier Ci is 1 by n. If there are n points summed over all, right, a Wj is essentially the weight belonging to the point. Weight, I told you, every point is given equal weights essentially. So weight of the point j into right, its prediction, right? So yj is actual thing. If the yj is not matching with the classifier's weight, classifier's decision, Ci xj is the classifier's decision, and yj is the actual decision, true label. If the label doesn't match, which means that only when the label doesn't match, the weights of that particular point get added up. So error. So if this is the notion of, this is the expression for error rate. So the weights of all the points which are misclassified will get added up to form epsilon I, and half of L of logarithm of 1 minus epsilon I by epsilon I. What is this? Have you seen this? 1 minus epsilon. What is this? It's actually like a weight normalized error, right? So if you can actually normalize this epsilon I parameter between 0 and 1, right, what will happen is it's very similar to the what you call, see, 1 minus zeta is basically, if pi is a probable, 1 minus zeta is the error rate, right? It's a value between 0 and 1. So basically 1 minus zeta will be like probability of correctness minus divided by probability of p divided by 1 minus p, right? If p is the probability of correctness, this is p, this is 1 minus p, logarithm of p by 1 minus p. It's odds ratio, right? You can essentially look, I mean, it's very similar to the odds ratio. So odds ratio of the probability of correctness, that becomes the error in the case of Adaboost. So that is basically used here. So for every classifier there is a weight, and based on the weight your classification is basically, everybody's decision is not treated equally in Adaboost. So what is happening here is you get this. And how do you update the weights? So you start with every training, I mean, you have got training data, everybody is alike, right? Then you take the decision, you know the weight, right? You know the weights. From the weights you can get the epsilon i's. So you know the first classifier's weight. And for the first thing, when there is only one classifier, when you start, you have t is equal to 1, which means that there is only one classifier, and you get a corresponding decision. And from that, you see that certain things are going wrong. What you do is you update the weights. How do you update the weights? The weight updated formula is like iteration, from iteration I to I plus 1. What you do is, right, you essentially normalize with an zi. What is zi? Zi is basically the normalization factor. Typically you can take the max of the value, and that's that's basically, if you look at it, into exp minus alpha I. What is exp minus alpha I? So this is a normalization, it's basically normalized previous weight into exp minus alpha I, all right, or exp plus alpha I. Understand this equation. If ci xj is equal to yj, right, for a point I am updating in iteration from, I'm moving from iteration I to I plus 1, I am updating the weight of a point. So where do you start? You start with everybody having the same weight, one classifier taking decisions, all right, and you know from the error rate of the classifier, you also know the the weight associate the classifier, so you can take the decision, and you have all these. Then how do you update the weights? So there'll be like, there's only one classifier, C1, right? C1, the point xj, I'm updating the weight for the point xj. I've told you every point is given a weightage. right? I'm updating the weight for the point xj. Ci, if Ci xj is equal to yj, what is the meaning of it? Which means that the correct Ci is currently, there is only one classifier now. So the first classifier, if the first classifier correctly classifies the points, what do? You need to bring down the error. So Vx e raised to, right, e raised to minus alpha I. And what is alpha I? You have only one classifier. You have one classifier, that's C1, so alpha 1. W, the previous weight normalized by maybe the max weight, right, or a constant, into e raised to minus alpha I, which is essentially saying you reduce the error if the correct classification happens, right? Reduce the error which is proportional to the weight of the classifier, right? I am currently considering classifier I, and if that classifier is making correct prediction of my label, what is going to happen is, proportional to the weight of that classifier, I reduce the weight of that point. Right? If that particular classifier is not making correct decision, right? I am at classifier I. Now I have only C1, right? At classifier I, if it is not, it's wrongly classifying the point, what you need to do is, based on the weight of the classifier, increase the weight. So essentially what this does is, based on the weight of the classifier, you either increase or reduce the weight. So let me do a recap. How does Adaboost work? You start with everybody having, every training point will be given a weight. You start with one classifier, right? And for that classifier, you can essentially compute this, because you got the weight and you know, like, whether the classifier is actually taking correct decision or not. You add up the weights accordingly with using the delta function. You get epsilon I, the error rate of the classifier. From epsilon I, you can compute alpha I, which is alpha 1. I have only one classifier, so I got alpha 1. From alpha 1, I can actually, I know, like, the decisions, and I know, like, so basically I know the decisions. So I have got all the points. Now all the training points can be classified as correctly classified or wrongly classified. What do I do now? I can actually increase the weight. It started with everybody having the same weight, so I can essentially increase the weight or decrease the weight. I have only one classifier, which means C1. If the C1 prediction is correct, what do? I have got a weight for C1, which is alpha 1. If the classification is correct, so from that equal weight, the weight will come down, right? Weight will be normalized, and e raised to minus the weight of that particular classifier will be used to bring down my weight. If the classification is wrong, you will increase the weight of such points. So for every point, you get a new set of weights, right? What do you do now? Once you have a new set of points, once you have a new set of weights, what you can do? Now, with a new set of points, you essentially, like, you can again train the classifier. You have the classifier. How do you do the classifier? You need all this, right? You need all this. So what you do is, you can essentially, like, do this. So you know the basically you can try to classify, right? You train the model. You have trained your model using that particular training data, same training data, and you essentially, what you do is, if it is not correctly classified, what you do is, you based on the incorrect classification, you get an error rate, right? From the error rate, what you can do is, you can compute the weight, and your classification is essentially here. You get the corresponding C, and from C you again update the weights, and you keep moving. So an example, right? If you have got H1 is correct on 15, this is a simple numerical example to understand the context. Imagine H1 is the first classifier, is correct on 15 samples and incorrect on 5 samples. That means epsilon will be 0.05. This is nothing but 5 by 15, right? 5 by 15 is 0.05. Alpha will be, you can look at that. Alpha will be half of ln into 1 minus epsilon. You get this number. So we can rewrite correct instance D2, basically, like, so the correct instance will have the weights updated, right? The new data set D2, the points will have the correct instance. All these 15 points, the weight will be, like, initially they all start with the same weight, right? 1 by 20, right? The correct points weights will be updated according to this formula, where basically you have chosen this as your constant parameter, and then you essentially, like, you do this, right? Essentially, what you can do is, this is basically, you reduce the weight of the correctly classified instance, and for the 5 points, as per this equation, the weight will go up. The weight will go up like this, right? So you have got, after that also, you got this data set. you train the model again, and on this data set, and you continue, right? So in essence, what I want to show is what I want to show you is yeah, this is a statement of Adaboost. You have a set of data points, labels are given here. Weak learning algorithm. Weak learn is essentially a classifier. It can be like, it can be a what do you call, a decision tree. It can be an SVM, whatever, right? I mean, slightly better than the random guess. And do, right, what you do is you train the classifier, you get back the hypothesis, and you get the notion of error, right? And you can actually like compute the weight. So alpha is represented in this algorithm as beta I. Then you update the distribution of the data set. You essentially what do you call, increase or decrease the weight, and then you keep continuing, right? Unless otherwise you have your convergence criteria, which is essentially like you got your error below, or you have done it for T classifiers or whatever. And the interesting part is, and this is one of the most celebrated algorithm, and this is not the only algorithm in boosting. This is just a representative algorithm. I thought just for the sake of for understanding, all I want to say is this is all about weighing training points in every other iteration based on whether they have done a good job, and the previous classifier has done a good job on those training points or not. If the previous classifier correctly classified a training point, its weight will come down. If the previous classifier has wrongly classified a training point, the weight will be increased. So the next classifier will take care of that, and will continue. This is called Adaboost. So there are other boosting algorithms, which is you can go back, look at it. There's something called gradient boosting, which is essentially you compute. Gradient is essentially you compute the residual, and you try to minimize. I mean, you train over the residuals. You add up a set of residual classifiers, and then residual learning mechanisms, and then you reduce the weight. So gradient boost is another boosting algorithm. Then there is something called extreme gradient boosting, which is also very interesting. So boosting is essentially all about what you call giving importance to the points based on whether they are wrongly classified or not. So there are two ensemble class of ensemble learning algorithms in the classification context. One is called bagging or bootstrap aggregation. Bootstrap aggregation is all about random samples of the same size created and multiple classifiers trained on that random samples, and then you try to aggregate those classifiers. This is called bagging or bootstrap aggregation. The other is called boosting. Boosting is giving him, I mean, basically you capture the notion of importance of every point, and refine that importance every other iteration, so that you get a better classifier, and you combine the decisions of this classifier. So you essentially, like, if you look at this equation, what you do is your classification function is becoming more and more complicated as you have more and more classifiers. As you go along, you are actually complicating the context of the classifier. Primarily, the model, the decision function is becoming more and more complicated, which means that you're trying to fix more and more training data, fit more and more training data into the classification context. Essentially, you're trying to reduce the bias. So Adaboost, we can say that is a boosting algorithm which works on the model complexity, because the complexity of the model is increased every other iteration with every other classifier. So that's why it's called, and so that your error rate on the generalization performance will come down. Essentially, you're working on in the boosting context, you're essentially working on making the training better. In the case of bagging, you're essentially trying to do the generalization better, right? So bagging works on variance side, and boosting works on the bias side, because it's all about making the model better by reducing the error rate, which is essentially you're trying to reduce that Z cap in the error expression, which is essentially the bias. So that's why it's called boosting, and these are interesting algorithms, and these are not only algorithms. This is just for your what do you call, university. And yeah, most of the, if you look at the literature, most of the winning algorithms are ensembles. So this is one example. Netflix prize was won by an ensemble, right? Netflix is essentially like, it was a what do you call, it's essentially a movie recommender rating thing. The grand prize was given, the 1 million grand prize. You can read about Netflix, and that was won by an ensemble which uses flavors of Kenyan and things of that kind. And another interesting example would be, if you look at it, let me see whether I can show you that. You can go and look at it. It's Squad, Stanford question answering data set, Squad 2. the Stanford question answering data set, and if you look at the leaderboard there, you can see that. So all these are ensembles. See, like most of these are ensembles. These are is essentially Stanford question answering data set is essentially a you are given a paragraph. Can you answer answer questions from that paragraph? So it's a challenge, running challenge, and people have gone beyond the human performance, which stands currently at 86, and the people have gone little above that, and you can see that who participates. This comes from all sort of Shanghai University, Salesforce, and even I think at times Google and all that, Google Research. They all participate in this challenge. And the interesting part is most of the winning algorithms are ensembles, not individual algorithms. So ensemble classification is interesting thing, and boosting in special and bagging in general are interesting. Bagging works on variance side of things because it tries to improve the generalization, and boosting tries to complicate the model in such a way that the error rate comes down on the training side, which is called which is essentially favoring the notion of bias, right? So ensemble classifiers are interesting. You can see that even the squad leaderboard, what do you call, the ensembles are doing better than the other ones, right? So I will be stopping recording here, and I will come back and cover the next topic maybe after a break.